Welcome to the calculation part of part B. You might note actually that we're quite close to solving part B already, just based on the preparation work we did in the earlier part of the exercise. So let's get started with the solution. What we want to find is the expected present value right before the beginning of the contract. So as given here, we need to calculate the expected value of the present value of the payment stream, where we take each of the payments, B of t, and discount them back to time 0, so t years. Now, the first thing that we can notice here that I think we should probably write over here in this side as a kind of almost a rule to remember is that let's see here, is that whenever we have the mean value of a sum of stochastic variables, so something that looks something like this, so whenever we have this, then we can actually interchange the summation and the expected value sign. And that is because, in essence, expected value is just a weighted sum of outcomes, or a weighted integral of outcomes, and we can always interchange sums and integrals. Well, for the most part, we can interchange sums and integrals at least as long as at least as long as the sum is finite, anyways. So we can interchange sums and integrals. Hence, we can interchange sums and expected values. So just remember that as a rule. Another rule that we should remember is that whenever we have the mean value of a stochastic variable multiplied by a constant, then we can take that constant outside the mean value as long as that constant is not stochastic in nature. So what we have here is we can take out the sum, and then we have the mean value inside, B of t, and also we can take out the e to the minus delta t. And the reason why we can do that is because the e to the minus delta t is not stochastic. The reason why I don't take b of t outside is because just in a second I will have to plug in the value of b of t, and we note that b of t depends on the remaining lifetime, which is indeed stochastic. So here I have the sum from 0 to k plus n, and now I can plug in the value of b of t, so I can just put the discount factor up front here, e to the minus delta t, and then I have the mean value of the payment stream, which was given as the indicator function of, so 1 if the remaining lifetime exceeds time t, and also 1 if the time t lies between k and is strictly smaller than k plus n, like this. And this here we can rewrite a little bit as well, because notice that we know that we can take a constant outside of the mean value. So anything that's deterministic we can take outside of the mean value. And the second indicator function has nothing to do with the uncertainty of the lifetime, so we can take that out. So we have the indicator function outside here. And then inside we have the mean value of the indicator function of the remaining lifetime exceeding t. And now in this next step I will do two things. The first thing is to notice that whenever we have the indicator function of some event, and when we take the expected value of that, well, then this is the same as taking the probability of the event. that the indicator function stands for. Another thing is that this indicator function outside of the expected value actually tells us that t must be greater than equal to k or strictly smaller than k plus n. That means that this changes the bounds of our sum to going from t equals k up to k plus n minus 1. So this indicator function goes into the sum, and then I change the mean value of an indicator of an event into the probability of that event, which is the probability that tx is greater than t. So what we have here is the conditional probability of survival, right? Because it's the probability of the remaining lifetime of an x-year-old exceeding t. And this is exactly tpx. So we have the sum from k to k plus n minus 1 of e to the minus delta t multiplied by tpx. So that's where we got to up here, and now we have expressed whatever we have in terms of tpx. The thing that we want to do now is to make this expression remind of this expression here. Now, just before we continue on, let me note that this result is not that surprising. Essentially what it just says is, take the payment at time k. There is kpx probability that it will be paid out, and then discount it back to 0. Then take the next payment at time k plus 1. Multiply it with the probability will be paid out and discount it back to 0, and just do that with all the payments. So it's kind of like a really intuitive way to understand this. So it's very nice that the formulas and the intuition, they follow. So in the next part of this solution, we will show how this expression evaluates into the expression of this.